Good evening, everybody, or good morning, or good afternoon, or good night, depending on when you're watching this video. This is Mr. Molikash, and this is our week 15 video for Math 171 online with Johnston Community College. If you're watching this video and you have any questions about what you see, you can shoot me an email right here. I teach online math classes at Johnston Community College in Smithfield, North Carolina. So the topic of discussion for this week are systems of equations. Now, what is a system of equations? Well, you might want to notice to start with that there's more than one equation going to be involved because the word equation is plural. So systems of equations means that there's going to be more than one equation, and we have to solve the solution that makes all the equations true at the same time. Okay, so for this week we'll be focusing on two equations. Later on you'll be dealing with three equations and three possible variables for the solution. So, okay, here's an example of a system of equations. Let me just give you a quick example. Let's say we have 2x equals 6. This is sort of an equation that is a system. It's only one equation, but the reason why there's only one equation is because there's only one variable. So this has one solution, x equals 3, right? So one equation, one solution, right? Okay, or one variable in the solution, I should say. So here's another system of equations, 2x plus 3y equals 7. Uh-oh, now there's an x and a y, right? 3x minus 4y equals 2. Okay, so we want whatever x and y numbers work in one equation, those same x and y numbers should work in the other equation as well. Now, if you were to graph, get a little envelope or something to cover this up. Let's say you were to graph this. This would be a line, right? Y equals mx plus b, you could get y by itself. And so there'd be lots of x's and y's that work in that line. In fact, there's an infinite number of them that make a line, right? But this would be a different line, and these two lines actually intersect, right? So if you were to graph these, you'd have your x and y axis, right? And, you know, one line looks something like this, and another line looks something like, I don't know, like this. And the x and y for the solution is this one point, because it's not just a point on one line. That same exact point is on the other line as well. Okay. Okay, now this, I will tell you what the solution to this is. The solution is x equals 2 and y equals 1. That's the solution. How do I know that that's true? Well, you could plug both of these in, both equations. So in equation 1, okay, you would try to do 2 times 2 plus 3 times 1, and you say, okay, does that equal, that's a question mark in case you can't read that, 7? And the answer is yes, right? 4 plus 3 does equal 7. But also, you want to check the other equation as well, right? So 3 times 2 minus 4 times 1, does that equal question mark 2? And the answer, of course, is yes, right? So since the x is 2 and y is 1 works in both equations at the same time, it's the solution to the system, okay? Now, regarding a system like this, there are some vocabulary words that you'll need to know, okay? So when the graph looks like this, when two lines are different lines and they intersect in one point, this is said to be consistent and independent. Independent, okay? So the two lines are independent of each other because they're not the same line. One line does not depend on the other one, okay? So these are not the same line. Okay, consistent means there's a solution. Solution exists, okay? So you might want to ask, okay, well, what kinds of systems of equations are inconsistent, or what kinds of systems of equations are dependent? So I'm going to give you an example of each one right now. All right, so remember, consistent means there's an answer, right? Okay, so let's say that we had 2x plus 3y equals 7 again, okay, and then we had negative 2x minus 3y equals 10. Okay, what would happen here is you'd be able to graph these, right? And your first line looks something like this. Okay. The other one looks something like this, and I'm doing some work off the screen. But okay, so let me label these. This would be the line 2x plus 3y equals 7. This is the line negative 2x minus 3y equals 10. All right, and you can tell that these lines are parallel. So, for example, if you get y by itself and do y equals mx plus b, you're going to get the same slope for both lines, but obviously different y-intercepts, right? All right, so this is an example where there's parallel lines where the solution is inconsistent because no solution exists. There's no point on one line that's also on the other line, right? There's no x and y that works in both equations at the same time. But independent because they are different lines. Okay, so inconsistent because there's no solution, independent because they're not the same exact line. So what do I mean by the same exact line, you might ask? Well, let's say that we have this example. Let's say that we have negative 4x minus, we'll keep the first line, okay, and we'll do something like this, right? So these two equations are actually duplicate copy of the same exact thing. If you graphed both equations, you get, this would be the first line, and this would be the second line. They're exactly the same line. And you can verify this by dividing all these numbers in the second equation by negative 2. So if you divide both sides by negative 2, sure enough, you get 2x plus 3y equals 7, which is the same thing as the first equation. So again, it's a duplicate copy of the first equation all over again. So these two lines are in exactly the same line, right? Well, is there a solution? Yeah, there actually is. The entire line is the solution because there's lots of different points that are on both lines. So the whole line is the solution instead of a single x-coordinate, y-coordinate point, right? So this system is consistent because there's a solution exists. In fact, infinitely many solutions exist. But these are dependent, okay, because they're in fact the same line. One line depends on the other one because they're the same line. So that's kind of what's going on with some vocabulary there. So there are a couple ways to solve systems besides graphing. So let me kind of go through two of them, two ways to solve a system. So let's go back to our first example. And this may be a little bit of a difficult example to begin with, but don't get scared when we have fractions or decimals going on. Okay, but this is our example, so we want to solve this, right? And again, I'm going to show you how to do this without graphing. So one way of doing this is by using what we call elimination. Okay, so elimination works like this. What you want to do is you want to be able to add the two equations together, but when you add two equations together, you eliminate a variable. Now, if you do that right now, if you add both of these right now, you're going to get 5x, and then you're going to get minus y equals 5. That doesn't really help us. We haven't eliminated a variable, right? We still have an x, we still have a y. So the goal in this is to try to finesse the equations, okay, so that you can multiply one equation through by a number, another equation through by a different number, and get either the x's or y's to cancel out. So this is what I'm going to do. I'm going to take equation 1, okay, and I'm going to multiply both sides of it by 4. Okay, so if I multiply 4 by everything, and I mean the right and the left side, then I get 8x plus 12y equals 28. Okay, well, why would I pick 4? Well, here's the reason why. There's a 4 in front of that y, and it's negative, right? So I think I can make that a negative 12 by taking this equation and multiplying it by 3. So whatever these numbers are, if you want to eliminate them, switch them around, and if these signs are different, make these the same sign. If these are the same sign, make these different, because the goal, as you'll find out, is to be able to add these equations together and eliminate a variable. That's the magic in this process, right? So now we can figure out that x is 2. And to figure out what y is, we can pick our favorite equation and plug the 2 back in. I like the first one because it doesn't have any negative signs in it. So to find y, I'm going to plug the 2 into that. And again, it doesn't matter. You can use any equation that has an x and y in it. I could use this one or this one. But, you know, just pick the easiest one to work with, right? There's no point in making the work unnecessarily hard. All right, so there's your answer is x equals 2, y equals 1. This could be written as an ordered pair like that, or you can just write it as x equals 2 and y equals 1. But both of these numbers are part of a single solution. So it's one answer, but 2 variables, okay? And like I said, later on next week, you'll have 3 variables or 3 equations, okay? All right, maybe you didn't like that very much. That was a lot of work going on there, right? You may have to rewind this video a little bit and slow me down a little bit. But there's another way to do this too, and it's called substitution. Substitution. Okay, so the way to do substitution is like this. You want to solve one of these equations for one variable, okay? So step 1 is solve one equation for one variable. So pick an equation and pick either x or y. Doesn't matter. I think I'm going to pick equation 1 and solve it for y. So let's do that. You did this in a previous math class or whatever. You know how to get y by itself, right? All right, so y is negative 2/3 x plus 7/3. So this equation rewritten now has y by itself. Okay, I took that first equation and solved it for one of the variables in it. And I could have solved for x instead of y, but we'll do that you know, this way this time. Okay? All right, so the second step is to substitute into the other equation. So we haven't messed with equation 2 yet, so I'm going to take this y and this y and substitute this y for this stuff. Okay, so I'm going to do 3x minus 4y equals 2, but y now is not going to look like it did before. It's going to be this equivalent stuff that equals y. Okay, notice now there's only one variable and one equation. So I'm going to be able to find x from this, and when I find x, I can put it back up here and find y, and I'm done. So let's work on this a little bit. Geez, this is positive 8/3, and this is negative 28/3. Okay, I told you not to get mad at me for the fractions, right? Okay, so this is 9/3 plus 8/3, which is 17/3. That's by adding the like terms. And then I have to add this to the other side, right? So that's 6/3. Now not minus, but plus 28/3. All right, so I have 17/3 x equals 34/3. And to get x by itself, I have to multiply by the reciprocal, 3/17, right? So the 3's cancel, the 17's cancel, I get x. Here the 3's cancel, and 34 divided by 17 is 2. Amazing. All right. So then, now you want to get the rest of your solution. So you put 2 up here, and I think you know what's going to happen. That's -4/3 plus 7/3, which is 3/3, or 1, right? So this is your solution. Okay, so that's, again, this wasn't the easiest example to work with. There are definitely easier examples in ALEKS or you know, in some other videos that you'll see in you know, the Week 15 weekly assignment folder. So, you know, don't fret because I gave you sort of a difficult example, okay? You'll get plenty of practice at this. Okay, the last thing that we'll need to talk about now is what happens when the two equations aren't lines. So, for example, if you have a graph where there's a parabola, maybe is one equation, and the other equation is a line, right? So a parabola and a line, when they intersect, there could possibly be 2 points of intersection. Maybe there's only 1 point if the line just touches the edge of the parabola, or maybe there's no solution at all, right? And so if there's no solution, remember what that's called? Inconsistent. Very good. Okay, so this is a consistent example, the graph that I just showed you, right? Okay, so what I'm going to have to do is I'm going to, you know, give you an example of, and this one will be a much easier example, okay? Yeah, this will be, I think, a much easier example, right? So, okay, here's what we're going to start out with. We're going to have a parabola, and we're going to have a line. And whenever this kind of thing happens, whenever, you know, the polynomials have different degree, like maybe that's cubic, that's quadratic, and God help us if that were the case, but this is just quadratic and this is linear. So we can solve this by doing the good old substitution trick. So for example, I'm going to take this x plus 1 and I'm going to put it right there. Or equivalently, I could take the x squared minus 2x minus 3 and put it right there. So basically what we're going to do is we're going to set these two expressions in x equal to each other. And you should know how to solve this, right? This is your good old quadratic equation. So you're going to set it equal to 0. So we'll get the right side to be equal to 0 by adding the opposite. And then over here we have x squared minus 3x minus 4. And always try to solve this by factoring. If you can't factor it, of course, you do the quadratic formula or completing the square, which I don't recommend on this one. But okay, so let's see, minus 1 plus 4. So we get x equals 4 or x equals -1, right? So how do we find out what y is? Well, we have two different y's since we have two different x's. So we could use either equation to find the y. I choose this one because it's a lot easier to work with than this other one, right? So what's 4 plus 1? That's 5. And what's -1 plus 1? That's 0. So there's two ordered pairs for solutions, 4, 5, and -1, 0. These are the two solutions to that system. Okay, let me show you graphically what that looks like by graphing this on the back. Okay, so the first parabola has a y-intercept of -3. Okay, its axis of symmetry is x equals 1. Okay, and its vertex is, let's see, 1, -4. So that kind of looks like this. Let's see. has zeros like this. Yeah. So yeah, the graph kind of does something that looks like this, and I'm doing my very best to draw an accurate graph. Okay. All right. So that's y equals x squared minus 2x minus 3. The line x plus 1, of course, has a y-intercept of 1 and a slope of 1. So that line looks like this. Okay, so that's the line y equals x plus 1. And you can see that there's 2 points of intersection, right? One's right there and one's right there. This is the point 4, 5. And this is the point -1, 0. And so these are the two solutions that we got when we did the problem. Okay, so that's, you know, an example of solving a system of a linear and quadratic together. Okay, so that's all we have time for this week. But again, don't forget my email address. You can also use the discussion board to ask questions to the whole class that I can chime in on. Have a great week.